Solve. A cruise boat travels 96 miles downstream in 4 hours and returns to its starting point upstream in 12 hours. Find the speed of the stream. Okay, we're being given a word problem. It's an application. It's called an application. Somehow we're going to apply a some kind of math theory. Perhaps we're definitely going to use a theory from physics to help solve this problem because it's about distance and time and speed. So sometimes it helps. We're reading the problem. And then we're also it helps sometimes to make a sketch. I'm going to try to make a sketch to help nail down a few things and make them more understandable for this problem. Okay, so if we are talking about a boat sailing perhaps on a river, it's a cruise boat, so I'm thinking, and there's the speed of a stream, and streams are usually have to do with rivers. So we have a starting point. The cruise boat is starting somewhere. Let's call it this point. And it's going to sail, it's going to navigate down the river to some destination. So here is the destination point. Destination point, or point of destination. Destination point. Well, a couple things. They're giving us some information. One of them is that the distance between these 2 points, the distance, d, is 96 miles. We have 96 miles between the starting point and the destination point. Okay, something else they're telling us here is that let's make this the boat. We'll make the boat. The boat is traveling at first. The boat is traveling with the stream. This is the boat's speed. Let's make the boat's speed be b. The boat's traveling. If the boat was traveling in water that wasn't flowing at all, it would be traveling with speed b. I'm assigning a variable, okay, to one of the unknowns. We don't know the speed of the boat, and we don't know the speed of the stream. But when they say downstream, when it's going downstream, the speed of the stream is helping push the boat. Here's the speed of the stream. I'm making it blue to think about water. Okay, when a vessel is traveling downstream, that means it's traveling with the flow of the water. Now, upon the return journey from the destination back to the starting point, the boat is going to be traveling what? Back to the destination, which means we're going to presume that the water is still, the stream is still flowing in the same direction, and they're telling us that when they say upstream. See this right here? Upstream. So what this means is now the stream is pushing against the boat. It's the same speed. The speed of the stream is pushing against the boat. So in the downstream condition, downstream means the boat is traveling with the current, and the current is helping speed up the boat. This circumstance, the boat is traveling upstream, and the speed of the current, the speed of the water, is slowing the boat down. These are the two situations that we're dealing with here. Okay, let's pull in for what I call the governing formula. Is going to, what we need to help figure this problem out comes from physics, and it's known as distance equals rate times time. I'm going to flip this around though, because it's going to help us make a table that might further help us out. I'm going to say rate times time equals distance. So in general, R is rate, like a rate of speed might be miles per hour. That's a rate of speed, your speedometer, mph, miles per hour. Time is the time that you travel at that speed. So when you multiply time, perhaps in hours, they better match. The denominator unit of time and the unit of time for this factor need to match. When you multiply rate times time, it's going to equal the distance that you've traveled. But we can know any two of these, not know a third one, and be able to solve for the unknown third one. So if rate is in miles per hour and distance is in time is in hours, then distance would be miles, measured in miles. All these units must agree to continue. Okay, let's make a table. The table that would help us describe the problem. I'm going to go ahead and let's see. Let's go ahead and show the table up here. I'm going to use this version of rate times time equals distance, where we have R and T on the left version, and we're going to make a table that'll hopefully help us. Tables are usually useful for summarizing information. So here's what we have: rate in miles per hour times time in hours. Let's go ahead and put these all in parentheses so we keep track of them. And distance is going to be in miles. It'll help us summarize what's happening here. So when we have two conditions that are going on, two circumstances, we have a downstream circumstance when the boat is traveling with the flow of the water. Then we have an upstream circumstance, which when the boat is traveling, pushing against the current of the water. So two things are about to happen. The actual speed, and I'm going to go ahead and I'm going to put these in colors so that they really match our sketch over here. The rate of speed, the effective rate of the speed of the boat when the boat is traveling with the current, when it's going downstream, what you have is the effect of the stream. The speed of the stream is helping speed up the boat. The speed of the stream adds to the speed of the boat. So the downstream rate is rate of speed, the effective rate of the boat, the R. The boat is effectively traveling at what it could do in still water plus the speed of the stream. The speed of the stream is helping. The other version of what the reality is that when the boat is turned around and it's headed upstream, the speed that the boat would be traveling at if the current wasn't flowing at all is B. But when it's traveling upstream, the speed of the stream is pushing back against the boat. So the speed of the boat in still water is being slowed down. The speed of the stream is slowing down. Slowing down is associated with subtraction. And so I believe B minus S would be the effective rate of speed of the boat. Now, in both of these circumstances, notice that the distance that we have, the distance is going to be the same. Look, either case, the boat is traveling 96 miles. But check out now the difference in time. Now I'm just going to go ahead and make this black. Look, when the boat is traveling downstream, notice this from the given problem statement. When a boat is traveling downstream, it only takes 4 hours to travel 96 miles. But when it turns around, look at how much longer it takes for the boat to go the same 96 miles. In the upstream circumstance, it takes the boat 12 hours to travel the same 96 mile distance. Here are the two realities. Look how much longer it takes. It takes 8 hours longer to get back through the same distance of 96 miles. What we're looking at here are two equations. And what we're going to create is the effective rate times time equals 96. This is equation 1. This is equation number, let's make this a column as well, equation number 1. And this second circumstance, if I say the effective rate of the boat times the time that it takes to travel the same distance, 96 miles, we're going to call that equation 2. If we were to solve these two equations simultaneously and end up solving specifically for S, that would be the goal of this problem. They want to know what is the speed of the stream. Some number, some speed in, I think, miles per hour. That's the answer to the problem. Okay, so let's write these out, and I'm just going to do it in one color for the moment. Okay, the first equation, B plus S times 4 equals 96. There's equation 1. Then we also have B minus S times 12 equals 96. Here's our two equations. I'm going to number them on the left. And I'm going to start solving them. Well, let's simplify them. Okay, I'm going to just simplify by distributing this 4. This equation yields 4b plus 4s equals 96. We just simplified the left side. This equation, when we distribute the 12 to both terms, to eliminate the parentheses, we get 12b minus 12s equals 96. There are a couple things we can do. If we use the elimination method, I want to use the elimination method to eliminate b. We would take, here's what I'm going to work on. Use elimination method. There's several methods. There's substitution method and there's elimination method to solve two equations simultaneously. I want to use the elimination method to solve a system of linear equations. These two equations in blue represent a system of linear equations. The exponents and the variables are 1, and we have two equations. I want to eliminate, I'm going to say to eliminate b. If we do, that would leave us with s equals a number. Here's how I'm going to eliminate b. I'm targeting the b in both equations, and I notice that 12 is a multiple of 4. If I could take this 4 and multiply it by something to make a negative 12, then add the resulting equations together, we would effectively eliminate the b variables, and that would leave and solve for s at that point, and we would get s equals a number. So here's what I'm going to do. I'm going to take this equation 1 and we're going to multiply it by negative 3, because that will generate a term. When I distribute this negative 3 to this 4b, look what's going to happen. Negative 3 times 4b. What we get is negative 12b. Now, I can't just do one of these, but what I'm looking at, just to show you at first, negative 12b is the opposite of positive 12b. When I add these equations together, we're going to eliminate the b terms, which is what this intermediate goal is. So, now we're ready to distribute the negative 3 to the positive 4s. Negative times positive is negative. 3 times 4 is 12s, and that's going to equal negative 3 times 96 is negative 288. Negative 288. And then we're going to copy the second equation. There was no need to transform that in any way. This is 12b positive 12b minus 12s equals 96. And now our goal to eliminate the b terms is going to be just to add these two equations together. So we're just going to add the two equations together. And notice that these are all lined up as like terms. So negative 12b plus 12b is 0. There's the elimination of the b terms. Negative 12s minus 12s, or negative 12s plus another negative 12s, would be negative 24s equals, and then we're going to go to our trusty calculator, and let's see, negative 288 plus 96 equals negative 192. Now 0 minus 24s is negative 24s equals negative 192. Now we're going to take negative 24s and divide by negative 24. Balance the equation by dividing the right side by negative 24. And of course, any number divided by itself is positive 1. S equals negative divided by negative. This is positive. That's going to make a positive. Let me get my pen back. Here we go. Positive 192 divided by 24 equals 8. And of course, this is the S we defined as the speed of the stream, and speed in this problem is being measured in miles per hour. So S is 8 mph, and that's the last thing we need to do is actually go up here now and select the appropriate response.